on at the moment. So for example, in this case, I chose to focus on the group that contain only even processes. So you can see in the value comparison window that only processes 0, 2, 4, 6, 8, 10, 12, and 14 are being compared. And you can see that all of them have the same value, that 0.25132. In this window, you can not only look at just a straight number comparison, but you can also look at the statistics. In this case, they don't actually give us any information because the variable takes the same value everywhere. But that statistical information can be important sometimes when you have particularly one task only that has a completely different value from the rest. Then you should have a significant variance from the distribution. You can also visualize the values across the different processes just by going to the Visualize tab, and that will give you, like you see, a very, very simple graph with the values at the different cores. Of course, this is mostly useful for the small core counts, but that's where you should start your debugging sessions anyway. Once we have arrays that are larger than one dimension, looking at values just by the numbers becomes very, very tedious. Unless you can come up with a good example that only has a 2 by 2 by 2 grid, things become pretty nasty when you have to look at 100 by 100 by 100 or 1000 cube problem if you want to go through every value. In this case, DDT allows you to look at values in a graphical way with what they call the multidimensional array viewer. The multidimensional array viewer is simply a way to ask DDT to evaluate an array of values that has dimensionality higher than 1. Actually, you can also view the values of a 1D array, but the purpose here is that you can go to very high dimensionalities. So essentially, you would have to specify an expression like the one you see in the slides. I hope it's clear enough, which is A and then bracket $I bracket $j. In this case, this is for C. If you were debugging Fortran, you would have to use the Fortran bracketing system instead of the square bracket. And then you will get one of these for each dimension that you have in your array. In these windows, in these little windows, you will set up the range that you want to look at. Once you're done, you have to hit the Evaluate button, and once you do that, that data table tab at the bottom will be populated with the values for the range that you have selected. Once you do that, that Visualize in 3D button at the very lower left will be enabled, and if you click it, you will be able to see something like this. So in this case, I just initialized an array, a two-dimensional array with a sine multiplied by a cosine to have something that looked a little bit nice. But the thing is that you can select any array that you have defined in your code and that is currently valid, and you can select any process where you want to see this. So this one showed you a comparison between processes, but if you choose a different process, in this case you can see that I have process 0 selected. You can see any of the other values. What you would have to do is you would have to go to the process group area in DDT. And let me go a couple of slides back to show you where that is. So at the very top, you see where the process groups window is. So you would select there whichever process you actually want to look at. And then when you go to the multidimensional array viewer, the information you would be seeing would be the one corresponding to that process. One thing that I want to highlight is that often in physical problems, people design codes with a very large number of indexes, often more than 3. So if you have an I, J, K, M, N system, how can you visualize that? Well, we only have 3 dimensions in a space, so you need to find a way to project all the other directions. The way that DDT does this is by giving you an option, and I hope you can see that line under the ranges that says aggregate function, which in this case is set to sum. And what this will do is will create a filter that allows you to filter out some of the dimensions of the array, or to collapse them using a particular mathematical expression. This is good not for you to visualize the values themselves, but more than anything to visualize patterns in your data. To visualize things like, okay, all my values look like a sine times a cosine, but I have 2 values which are completely out of range, and instead of being between -1 and 1 are 256 times 10 to the minus 350. So that's where the visualization tool is very useful, to find out these outlier values that normally indicate that there's a problem in your code. So like I said, you can change this, the visualization from one process to another by changing your selection in the process control window. Now, analyzing memory usage. So far I've been talking about analyzing data just by looking at the data itself. But very often we want to know what is our memory usage in terms of how many function calls we've made to allocate memory, how many function calls we've made to deallocate memory, because we want to make sure that we're not forgetting to deallocate memory at some point, or we simply want to know how much memory each task is using at a given point. For this, DDT gives you 2 options: current memory usage and overall memory stats. So if we look at current memory usage, you will see, in this case, probably I should have come up with a better example, but you will see a pie chart of all the processes involved in your calculation. It doesn't have to correspond to all the processes, that's the default. You can select just the top 5, 10, or whatever you want to select. And in this case, what you can see is that process 0 is using a lot of memory, significant amount of memory, more than the others. So unless I know that this is the intended behavior of the code, my first suspicion is that process 0 is not deallocating memory at some point in the code, and I would immediately focus on that. So this is a pretty powerful tool. Also, if you go to table view, it will give you all sorts of details about how many arrays have you allocated of which sizes and so on. But the visual part of it is very helpful in an initial state. Regarding the overall memory stats, you can look at both size and number of calls. Size is, this example is for a different code than the one I just showed you, because you should realize quickly, because all processors are allocated the same amount of memory. And size for me in particular is not as interesting as the total number of calls. So in this case I can see that everybody is making roughly the same number of allocation and deallocations, which makes me quite happy, because this code was supposed to be doing this. All tasks were supposed to be doing exactly the same amount of work. But this part is quite useful if you see that there are very big differences between different processors, and that's not the intended behavior. In that case, you can very quickly try to find out what the actual problem is. Also related to memory, although this is not something you're going to do yourself, just looking for the problem, is the way that DDT tells you when a segmentation fault happens. If you look at that message in detail and you actually read through it, you will see that DDT tells you exactly the line of the code where the problem happened, line 87, and it tells you the reason. It says this address is not mapped to the object. So in this case, most likely, I'm essentially trying to access beyond the limits of an array that I have allocated. And this level of accuracy, you would never get it by just trying to do a manual debug. And although this is not particular to DDT, all debuggers will give you this level of accuracy, it's very good to know that once you set up that memory checking, you will get all this information. Now I'm going to go very, very quickly over message queues, because this part is really only helpful when you have very small codes. Well, small in terms of tasks, MPI tasks. Message queues will give you a visual layout of your communication, which is broken down in three separate queues. There's the send queue, the receive queue, and the unexpected queue. The unexpected queue contains all those messages that have been lying around in the system for a while and nobody has completed. These are typically messages that have something wrong in their arguments of the function call, so that they cannot be completed because there's no message matching them, or because we have made some type of blocking communication in a pattern such that everybody is sending but nobody's receiving, or everybody is receiving but nobody's sending, and because we're using blocking communication, there's no way we can get out of the problem. So one of the very important things you want to watch out for here is the unexpected queue. Messages which are in the expected queue are usually not that much of a problem, although they could still be if you did something wrong with your argument. One thing that I don't think shows very nicely on this screen, but you should be aware of, is that on the bottom left there is a little tick box called Show Queues in Table. What that will do is open a fold-out that will show you a table with all the messages that are still pending, sent, and have been exchanged, their sizes, their sources, and their destinations. So if you don't have tons of messages, that's also a good source of information for debugging. And in terms of how to use DDT for a fairly regular and complete debugging session, this is pretty much all you need to know. So what I'm going to do now is I'm going to stop for a minute, see if there are any questions, and after that I'm going to do an example debug session with a code that we have that has several bags put purposefully in it. Do we have any questions from the audience? Yeah, I can see a hand there.
Yes, we have one. Hold on. From NCSA.
I was just wondering how easy it is to find, let's say, floating point exceptions using DDT. Like, can we find the? I'm sorry. Can we find the exact location where the floating point exception occurs within the code?
Yes, you will pretty much get the same information as for a segmentation fault. So it will tell you the line where it happened, and it will tell you it's an arithmetic exception instead of a seg fault.
UCLA has one